So now let's see how we can construct DFAs for specific languages, right? So we will see different examples. So how can we construct a DFA for this language? L1 is a language which accepts a single string ABA. So start with the start state Q0 or Q0, and if you keep reading these characters in order, you keep moving forward to different states. If you read an A, you move forward to Q1. If you read a B, you move forward to Q2. If you read an A, you move forward to Q3. And after reaching Q3, you can accept this string. So you make Q3 a final state. And now, in all these states, if you read A, you move forward. If you read B, you move forward. If you read another A, you move forward. But for these states, you have to mention what if you read other symbols, right? Because we have to mention for every state and every symbol. So if you read a B at Q0, you have to reject it. So how can we reject? We send them into a different state, Q4, which we call basically a trap state. Okay. So all these are trap state because we have to reject. We just say it a trap state and just keep looping there. Okay. Similarly for Q1, instead of B as your second character, if it reads A, you go to this trap state. Again for Q2, you go here, and for Q3, after reading A, B, A, you will enter Q3. But after entering Q3, you cannot read any more characters, right? Because only ABA is allowed. So if you keep reading more characters, this also you send to trap state. So a trap state is basically it just keep looping only over there. It will never reach any final state. So that's basically a trap state. So look at this DFA. It is pretty obvious like why this DFA will only accept this one string, right? Okay, so let's move to the next example. So L2 is a different language which accepts two strings exactly, which are basically ABA and ABB. So how can we construct a DFA for this? So this DFA will be very similar to previous one. So let me copy it. So copy and paste. Okay, we'll just draw it again. So start with the start state Q0, and if you read, so what you have AB common in these two strings, right? So for AB you move forward as usual. If you read an A, you move forward, and if you read a B, you move forward. But after that, you can move forward if you read either A or B. So You can write it this way. If you read either A or B, you can move forward to Q3 where you can make it a final state, and then we'll still need a trap state here, Q4, because for other states we still have to write the rejections, right? If at Q0 it sees a B, you have to reject, and Q1 if it sees A, you have to reject second character, right? For A it will move to Q1, but after reaching here it has to see B, but instead if it sees A, you go to trap state. And for third state Q2, you already mentioned for A or B, you definitely go to Q3. But for Q3, you have to go to trap state because you cannot read any more than three characters, ABA and ABB. So if you read any more characters after that, you go to trap state. Okay. So again, this is a DFA for this language L2, and this accepts only two strings, ABA and ABB. Rest of all other possible strings, they will never end in Q3 at the end of reading the whole string. Okay. So let's look at more examples. So look at L3. L3 is set of all strings x such that x start with 0. So what all strings that start with 0 1? Like for example 0 1 starts with 0 1, 0 1 1 starts with 0 1, 0 1 0 1 starts with 0 1. So set of all such strings that start with 0 1, your language is set of all such strings. So how can you construct a DFA that accepts all such strings? So start with the start state Q0. So if you read a 0, you keep moving forward. But if you read a 1, you reject. So add a trap state. And from Q1, if you read a 1, you again move forward to Q2. And if you read a 0 instead, you go to trap state. Right? And after reaching Q2, so you have to accept all strings that start with 0 1. So if you reached Q2, that means your string just started with 0 and 1, right? Because only if your string start with 0 1, from Q0 you will reach Q2. So after that you can keep reading any characters. So after that you will stay here. You can keep reading as many characters as you want. So this is your DFA. Call this Q3 trap state. So for every state you have to mention for 0 transition and 1 transition where it goes, right? So again, this DFA accepts every string that starts with 0 1, right? Let's look more examples. So let's look at this. L4 is set of all strings where length of string x is even. So how can you draw DFA for that? So what you can do is basically you start reading the string x. So initially you haven't read any character from string x. So the number of characters you have read till there is 0, and if you read your string every character one by one, your length keeps increasing. The length of string that you have read till there, so it will become 1, 2, so on till length of string. So what can you do to make sure you accept strings of even length? So start with the start state q0 and keep another state q1. So empty string has length 0, right? So you have to accept empty string since it's of 0 length and 0 is even. So you make start state as accept state. But if you read one more character, your length of string becomes hard. So you move to this state 0, comma 1. And q0 basically represents even length strings and q1 represent odd length strings. So again, if you are at q1 and you read one more character, your odd length string becomes just even for reading one more character, right? So this state represents set of all strings that you have read till there are of even length. So this is your DFA for this language. Similarly, what will be the DFA for this? This is basically same as this, where instead of q0, q1 will be your final state, right? So if you read one more character from start state, your string becomes odd. But if your string is odd and you read one more character, it becomes even again. So it will switch between even to odd and odd to even for reading every character one by one. So this is your DFA. Okay. So now let's look at another example. So L6 is a language which accepts all strings of this property where every string's length is of the form 3n plus 1. So basically every string length can be of the form what? It can be either 3n or 3n plus 1 or 3n plus 2. So if the length of string you read till there is 3n and you read one more character, your length just became 3n plus 1. And from 3n plus 1, if you read one more character, your length will become 3n plus 2. And the string you read till there is 3n plus 2 length. And you read one more character, your string will become 3n plus 3, which is basically 3n, right? So the states of our DFA will be these. Q0, Q1 and Q2. So you start state Q0, your string is of length 0 for epsilon. But if it reads one character, any one character, it goes to Q1 where length of strings read till there is of the form 3n plus 1. and if you read one more character it will go to Q2, and again if you read one more character it will go to Q0. So Q0 represents all strings. So Q0 represents all strings that you have read till there have length 3n, and from there if you read one more character your string's length will become 3n plus 1, that will denote by Q1, and from 3n plus 1 if you read one more character your string length becomes 3n plus 2, so it will go to Q2, and if you read one more character it will go back to Q0. So what will be your final state in this case? You want to represent all 3n plus 1, so Q1 will be your final state. So let's look at another example. L7. L7 is a language which is set of all strings x such that x has last second character as 1. So this is basically set of all strings whose last second character is 1. So how can we construct a DFA for this, and what will be the states basically? So only way you can do this is by using, you keep track of all the possible last two characters. So what are all your last two characters possible? 0 0 0 1 1 0 1 1. So like if you are given a string say 1 1 0 1 0 1 0 0. So if you keep moving, reading character by character, you can keep track of last two strings you have read till there. Like for example, if you have read till here, your last two characters are 1 0. But if you have read till here, your last two characters will be 0 1. And if you have read till here, your last two characters will be 1 0. And what if you have read only first character? What will be your last two strings, last two characters? There is only one character, so there is not even a second last character, so you will have to reject it. So what we can do is just put a padding of 2 zeros here. We want to see last second character as 1. So rejecting for not having a last second character is basically same as putting 2 zeros at the start, because if you are given an empty string then it has no characters. So if you put 2 zeros at the start, then for reading empty string, what will be your last two characters? Basically 0 0, and your last second character is not 1, so you can reject it easily. And if you look at strings of length 1, like only 0 or only 1, you don't even have any last second character, so keeping a padding of 0 for reading till this whole string, your last two characters will be 0 0, and this is not 1, so you can reject. For this also, if you maintain padding of 2 zeros at the start, for reading this string 1, just 1, your last two characters will be 0 1. So what we will do is for every given string x that we need to verify, just put two zeros at the start and keep reading the x string character by character and keep track of every last two characters. So you have these as your possible last two characters, right? So you make those your states. So 0 0 0 1 1 0 1 1. So at the end, if you end up in any state, like if you end up in 1 1 state or 1 0 state, they have last two characters as 1. So at the end, if you end up in any of these two states, you will accept. So you make these two as final states, right? Because out of all these four, only these two states have last second character as 1. So again, these states are basically for reading the string till there, what will be your possible last two characters. So these are all the possible states. Again, you when you started the string, you have a padding of two zeros. So when you start, these will be your last two characters, 0 0. So that will be your start state. Now draw the transitions. So currently your last two characters are 0 0. And if you read an additional 0 as new character, what will be your last two characters now? This became this. So you write for reading a 0, your last two characters will still be 0 0. But if your last two characters are 0 0 and if you see a new character 1, your last two characters just become 0 1. So you write for seeing a 1, when you are at 0 0, you will move to this state. Again, similarly for all states. If your last two characters are 0 1 and you read a new character 0, your last two characters become 1 0, and if you read a 1 instead, your last two characters become 0 1 to 1 1. So you go to this state for reading a 1. So similarly for these also, write down. So for 1 0, if it sees a 0, your last two becomes 0 0. But if it sees a 1, your last two characters become 0 1. And if you are at 1 1 and you see an additional character of 0, your last two become from 1 1 to 1 0. So from 1 1, if you see a 0, you move to this state. But 1 1, when you see a new character 1, your last two characters will still be 1 1. So for reading a 1, you will stay there. So this is your DFA that accepts this language. It has one start state 0 0 and two final states, these two, 1 1 and 1 0. So every state represents, in this case, last two characters you have read. are seen in X. Till the point you read. Right? So every state represents till the point you have read what are the last two characters. So at the end, if if you end up in these two states, 1 0 or 1 1, your last two characters are 1, so you accept those two states only. Okay. So now let's move on to a different example. So now let's look at this example. So L8 is a language which is a set of all strings X such that X is a binary representation of all numbers divisible by 3. So if we know that, like, how can we solve this? So what are the states possible? States are basically in this case for if you divide any number by 3, what are your possible remainders? 0, 1 and 2. So we will have 3 states Q0, Q1, Q2. So they are basically if you have read till some part of string, if its remainder is 0 it will stay in Q0, but if its remainder is 1 it will be in Q1 state, and if its remainder is 2 it will stay in Q2. That's how we construct the states, where Qi is basically if the string you read till there, if its remainder is 0, if its remainder is I, then you will be at state Qi. Like for example, if you are given string 1 1 0 1 0 1 1, so before starting reading, your string is basically just 0. So what's the remainder when you divide 0 by 3? 0. So your start state will be Q0, and then you will have Q1, and then you will have some Q2, and we want to only accept strings that are divisible by 3, so only Q0 you will make your final state, because if you have read the string you have read till there is remainder 0, only Q0 has that. For Q1 it has remainder 1, for Q2 it has remainder 2. So now how do we make transitions between these three states? So let's see for Q0. So you have read some string till there and your remainder is 0. Now if you append another 0 at the end, what will your remainder to 3 become? So when you append a number 0, You are basically doubling the previous number, right? Right? If for a given binary representation, if you add a zero at the end, it is basically same as doubling that number, right? But if you add a 1 at the end, this is doubling previous number and adding 1. So now how do we make transitions between these? So let me rewrite this again. Q0, Q1 and Q2, where Qi is basically what is the remainder of the binary string you read till there. If it is 0, you will be at Q0. If it is 1, you will be at Q1. If it is 2, you will be at Q2. So, and you will only accept strings that are exactly divisible by 3. So, remainder 0. These strings you will accept this state. So, how do you write transitions now? So, using these, if your previous number is divisible by 3, like assume you are at Q0, so your number is divisible by 3. So now if you add a 0 at the end, which is basically doubling the number, so your number is still divisible by 3. So your number will still be, your remainder will still be 0 when you double the number. So for 0 you will stay at Q0. But for your previous number, if you add a 1 at the end, or 1 transition from Q0, your remainder will become 1, right? Because your previous number is divisible by 3. Adding 1 means you are doubling that number, which is divisible by 3, and adding 1. So your remainder will become 1. So you will go to Q1 for reading 1. Now for Q1 and Q2. So for Q1, if your previous remainder is 1, and if you add a 0 at the end, what will your remainder become? So your previous remainder is 1, and if you append a 0 at the end, your 3 remainder will become double, because when you double this number, your 3 remainder doubles and you are adding 0 at the end. So your 3 remainder will be 2. So for reading a 0, you will go to state Q2. But for reading a 1, so your this number has already remainder as 1 and divided by 3. So when you append a 1, your 3 remainder will become double of 1. This will be doubled, and this will add a new one. So which is 3. So 3 remainder will become 0. So for Q1, if you read a new character 1, your remainder becomes 0. So you go to Q0. And now for Q2. So if your current number is remainder 2 when you divide it by 3 and you add a 0, so your 3 remainder becomes double plus 0, right? Because when you add a 0, this number is doubled So this will be 4. That means remainder is 1. So for a 2 remainder number, if you append a 0, your remainder becomes 1. So Q2 upon reading 0, it will go to Q1. And what happens if it reads a 1 instead? So this will be 2 times 2 plus 1, which is 5, which is 2 mod 3. So Q2, if it reads a 1, it will stay there because it got remembered to again. So how can we write this in more mathematical way? Transition function. So delta of, say you are at a state Qi. Say you are at a state Qi, and then you read a new character A, where A belongs to 0 or 1. So which state will you go to? Q of. So your previous remainder will always be doubled 2 of I plus whatever character you are adding, either 0 or 1, that will also add up mod 3. So you can write your transition function this way, and this is your DFA. So this and your previous example 7, these are not trivial examples. You have to identify what possible states and then draw the transitions between them. Okay. So you'll stop here. Okay, so let's look at some more examples. So the main goal of these examples is to help you gain some understanding on how you can construct DFAs for different languages on your own. Okay, so for every DFA, let me write. For every DFA that you construct, first make sure whatever states you are having, make sure you mention for every state, mention transition for every character or symbol. For reading every symbol in sigma set, you have to mention to which state it goes. Either it can go to a different state or it can stay in that state. You have to mention for every symbol for DFA. And again, mention a unique start state. Right? There is exactly one start state for every DFA. And also mention final states. Okay. Every DFA has all these things. Okay, so let's look at the current example. These examples will just help you build some your own understanding of so you can be able to build DFS on your own. So let's look at this example. L1 is a language where every string starts with AABA. So how can we build a DFA that adds up only these particular strings? So we seen this example before. Start with one start state Q0, and only if you read AABA you keep moving forward. Yes. If you read an A, you move forward. If you read another A, again move forward. And then if you read a B, again move forward. And after reading AABA at the start, you come to a final state. And if you keep reading more characters, once you reach this state, it's okay because you only need to make sure you started with AABA. And then after this, you can just stay here forever. But for these states, if you read anything other than AABA, you will go to a trap state. This is a simple example. So you write transitions these and name your states Q1, Q2, Q3, Q4 and Q5. So this is a simple DFA. So now let's look at another variant of this problem. So L2 is a language which contains all strings x such that this is x such that x contains AABA as a substring. So what is a substring? If you have some string like this is your substring, this is another substring. So any continuous string of characters inside your string, that can be a substring. Your whole string can be a substring of your string, and epsilon can be a substring of your string where you choose no characters. Yeah. So how can we see if AABA is a substring of your string? So what we will do is again start with the start state, and let me just write down the DFA and explain. You keep moving forward again. And in this case, you will not go to a trap state for every time you reject, because this DFA, what it does is it goes through the given string x from left to right, and it will go to a final state only when it sees the first ever AABA substring in your string. It just has to identify one of the AABA substrings in your string, then it has to accept. So this DFA will actually look for the first occurrence of AABA in X. So let's do this. So if it reads an AABA straight, it will enter a final state, and after that we don't care, so we just stay there because it has read some AABA. And if your string starts with B at start state Q0, let's give names. So instead of A, if at Q0 your string starts with B, you just stay at Q0. And again, what these individual states represent, let me explain. So Q0 represents your last characters till there are either Q0 represents last characters are either B or epsilon. Again, let me write and explain. Q1 last characters are A, Q2 A, Q3 AAB, Q4. Let me explain once after I write. So these states are basically, in this case, they represent, if you are at Q0, that means the last characters you have read till there, like after you keep transitioning, if you ended up at Q0 at some stage in the middle of X, that means that your last characters you have read either are, either it's an empty string or B, your last character. And if you are at Q1, that means that your last characters are A, and before that will be either B or epsilon. And if you ended up at Q2 at some point, they mean that your last characters are definitely AA. So if you look at it this way, now draw the transitions for all the other states. So if you are at Q1 and you see a B, so what will happen? If you want to see an AABA next, you have to start from Q0 again, right? So you go here, and if you are at Q2 and instead of a B, if you see an A, that means your last two characters are AAA. I mean, your last three characters are AAA if you see an A. Okay, let me explain. So if you are at Q2 and see an A instead of a B, your last two characters are currently AA. But if you see an A, they will be AAA. So if you want to see an AABA next, you just have to see a B. So you just take these two and just stay there. And now let's look at Q3. So after Q3 represents that your last characters are A, and B, but instead of A, if you see a B, you have no choice but to again start with A, B, A. So if you see a B, you just have to go to the start, right? But if you do if you do see an A, you will eventually reach to Q4 and you will accept. So just look at it for a while, you will understand. So and next example is L3 is a language where all strings end with AABA. So what does it look like? Let me just copy the previous DFA. So what changes do we have to make here? This observes that in the previous case it is looking for in L2 we are looking for first occurrence of AABA in the X, but in L3 here we have to make sure that our string ends with AABA. So what changes do we have to make? First of all, look at the final state. Let's erase the transitions further. So if you are at a final state and if you see an A, what does that mean? Final state means that you have read A, B, A till there, right? But if you see an A, where will you go? You have to go to the state which ends with A, right? Because then you can see B, BA and just move forward, right? Because if you see an A, you just have to see next BA, right? So if you see an A, where will you go? You go to Q2, right? And similarly, if you see a B, A, B, A, B, you have no choice but to again start with A, B, A, because with A, B we cannot do anything. But in this case with A, you can just add B, A. So if you see a B, you go to the start state. So what you have to do is just construct a DFA and make sure that it only reaches, like for a given input string X, if we want to verify, make sure that only strings that follow this rule will be accepted into the final state at the end, right? Make sure that your DFA just does that. Every string you try that should be part of your language should end up in a final state. That's how you have to just construct a DFA. Okay, Let's look at even more examples. Okay, so let's look at this. This is a simpler example. Okay, so L4 is a language. It's a set of strings X such that X contains even number of A's. Or like you can write this in a different way also. Set of strings A power n such that n is some 2k for all k greater than equal to 0. And k is a k belongs to whole numbers, right? A simpler way where A power n is basically where A power n is just a written in tens. So how can you construct a DFA for strings like this? So it's a simple example. Again, in this case, you are considering your alphabet sigma as exactly single element, which is just A. So this is an easy example. You start at the start state Q0, and currently if you are at Q0, that means you have read no characters yet. So if you are an empty string, you have to accept it, because for k equal to 0, a power 0 is empty string. That is part of your language. So accept it. And if you read one more a, you will move forward to a different state q1. And now your string is of length 1, just a, right? But if you are at q1 and you read one more a, your string length became just 2. So you have to accept it. So you just do that by coming back. So if you are at q0 and you read a character a, your string just became of odd length. So you move to q1, and if you are at q1 and you read one more character a, your string length will become even again. So you can come back to q0. So this is a simple DFA. Now what can we say about language L4.5, which is basically odd length strings. So you can write it even simpler. A power 2k minus 1, where for all k belongs to natural numbers, right? And again we have one alphabet. So what does DFA for this look like? This is simple again. You just have to accept q1 as the final state in this case, because q1 represents set of all odd length strings, right? If you ended up at q1, you have read exactly odd number of a's, right? If you look at string single a, start at q0, you will reach q1. You will again reach q1 if you read odd number of a's, right? If you read one a, you will move to q0, and you read a next a, you will move to q1 again. So it will accept only odd length strings, right? Let's keep looking at more examples. So look at L5. L5 is a set of X such that X contains even number of A's. But in this case, your sigma is A and B. So how can you construct a DFA like that? So again, just copy paste or DFA. So you have to just include transitions for B's. So what happens to any state if you see a B? What happens to your string if it contains B? We will not throw them away. We just ignore all the B's, right? I just mentioned that X contains even number of A's. So it's okay to have a B, but we just have to make sure our A's are of even count. Okay. So at both states you just stay there if you read a B, right? Can you understand like why this represents this particular language? That's the whole idea. Okay. Now let's look at L6. So L6 is a language where every string contains odd number of A's and always ends with a B. So how can we do that? Again, we just copy paste our previous DFA. So in this case, we have to see that every string contains odd number of A's and ends with a B. So again, you can write it simpler way. L6 is A power 2k minus 1 B, right? Where you don't have to write where k belongs to natural numbers. Here also we can, yeah, this is meaningless. This for all symbol. Okay, so let's see what we can do here. So how can we solve this or modify this DFA? So again, you remove Q0 as your F substate. So if you are at Q0 and if you see a B, that means that your string will be of form A power 2k and B, and you cannot accept that. So if you see a B when you're at Q0, you send it to a trap state. But if you are at Q1 and you see a B, what you have to do? You send it to a different state which you can accept, right? But it will be of the form 2 power A power 2k minus 1 and B. But after this you cannot read any more characters. So if you reach Q2 and you read any more characters, you will go to trap state. So understand again why this DFA is actually representing our particular language. You just look at what possible paths any string can take to reach Q2 state. Only these strings will finally reach Q2 state. Right? Just understand that. And let's look at final example. So L7 is a language where every string contains even number of A's and odd number of B's. So how can we do that? So let's just do the even number of A's part first. And okay. And again paste another version. So let's change the names of these states. Q2, Q3. So what we can do here is basically, okay, let me redraw the whole thing. Okay, so let me draw the DFA and then explain. Q0, Q1, Q2, Q3. So one start state. I will explain after constructing this DFA. Okay. So these states represent basically if you start at Q0 and if you see an A, you move to Q1. And similarly, if you are at Q1 and see an A, you move to Q0. And also Q3 and Q2, they will switch between themselves for seeing A, right? And these transitions, look at this, they are basically, so this is one particular portion and this is another particular portion. So if you are in Q0 or Q1 and you see a B, you will move to either Q3 or Q2, right? Like for seeing a B, you will keep moving between these two. Like if you call Q0, this is some stage 1, this is a stage 2. For seeing A's, you will keep moving between within the stage itself. If you see an A, you keep moving between those two, right? But if you see a B's, you will move from stage 1 to stage 2 or stage 2 to stage 1 back. If you see, right, a B. So how can we, so which one will be your final state if you see even number of A's and odd number of B's? Let me erase. So think about it. What will be your final state if you see and even number of A's and odd number of B's. So Q3 will be your answer, because if you see an even number of A's, you're either in stage 1, you will be at Q0, but if you're in stage 2, you will be at Q3, right? And for seeing odd number of B's, you will stay in stage 2, right? If you see even number of A's, you will be in either Q0 or Q3, and odd number of A's, you will be in either Q1 or Q2. But if you read even number of or odd number of B's, you will be in stage 2, right? And if you read even number of B's, you will stay in stage 1, right? Just look at this, you will understand. Just think about it. And similarly, if you want to consider the language where A's are odd and B's are even, what will be your final state in that case? Q1 will be your final state, right? Because if you see odd number of A's, you will be either in Q1 or Q2. But if you see even number of B's, you will be in stage 1, so you will be end up in, you will have to make Q1 your final state if you want to consider DFA that represents odd number of A's and even number